My name is Harald Etschmeier and I'm probing new approaches to lead-free die attach. A die attach is a process step in semiconductor manufacturing. The process line is generally divided into two parts, the front end of line and the back end of line. The front end, where the silicon wafer is treated as a whole, ends with the dicing of the wafer, where the chips or so-called dies get separated by a diamond plate or a high-power laser. The die attach is the first of the three process steps in the back end of line. The chips are picked up from dicing foil and bonded to a conducting substrate, the so-called lead frame. The second step is wire bonding. An electrical connection is made to the front side of the chip. Fine gold or aluminum wires are fused to metal pads on the front side of the chips by ultrasonic vibrations. The connections can be made between chip and lead frame or multiple chips. The last process step is to encapsulate the chip in a molding compound, insulating it electrically and protecting it from its environment. Now the chip is finished and ready for assembly on a circuit board. Die attachment seems to be a relatively simple procedure, but the requirements are high and quality is critical. Because every chip is handled individually, it has to be a cheap process with high throughput, so that the thousands of chips on a wafer can be processed in a reasonable time frame. For my experiments, I'm using a lab-scale die bonder, which has much lower throughput but allows much more flexibility in the process parameters, such as time, pressure and temperature. Recently, new challenges arose, which make this standard process no longer viable. These include thinner chips with thicknesses in the order of tens of microns. Also, new regulations, such as the restriction of hazardous substances, forbid the use of lead in electronics. One approach to overcome these challenges that I follow in my work is the use of nanoscale silver paste as a solder material. It's based on the fact that the melting point of a metal is significantly decreased when the particle size approaching the range of nanometers. In the paste, the particles are stabilized by a dispersant that has a polar acid function in the one end and a hydrocarbon chain in the other. Upon heating, the organic molecules decompose, the silver particles get in contact and the sintering is initiated. This is a scanning electron micrograph of the paste as it is applied to the silicon wafer. Upon sintering, the particles emerge to form a porous structure connecting chip and lead frame. Another approach I'm following is diffusion soldering. For this method, the interconnect material is directly deposited on the wafer backside by either electrochemical plating or physical vapor deposition. It consists of a layer of high melting temperature metal like copper and a layer of low melting solder like tin. When the chip is pressed on the hot copper substrate, the tin is melted and by diffusion of copper an intermetallic compound with a higher melting temperature is formed, so that it is solidifying isothermally. This intermetallic compound formation can be followed by focused ion beam microscopy and in situ X-ray diffraction. This method allows it to follow the development of the different intermetallics in real time. Scanning acoustic microscopy can be used to detect voids in the solder joint. And shear test yields information on the physical stability. The goal of my thesis work is to find an interconnect method that can push the limits of device performance.